Okay, so we're going to just talk about factoring to change how expressions look. So you remember how when we had an expression before, I think you've seen expressions like this back in Algebra 1A, and it looks something like this. You might have had like, let's say we had 8x minus 28 divided by 4. So we want to simplify it or find a way to make it different, and what we did was we looked for the greatest common factor in this numerator together, which happens to be 4. And then I factor that out, right? So 4 times 2 is 8, so that would be like 4 times 2x, that would give me the 8 right here, right? The 8x if I had that. And then this negative 28, I asked myself, well, what does 4 have to be multiplied by to turn into 28? Well, 4 times 7, right? So that's 4 times 7 is 28. Negative 7 will be negative 28, right? So these two expressions are the same, and then because I'm dividing by 4 and multiplying by 4, those cancel, and so we find out that expression is the same as 2x minus 7. We just simplified, okay? So now what we're going to do is we're going to do some work, and in the next adventure you'll figure out kind of a little more reason why. But we're just going to do some work, and we're going to take trinomials that involve squares, and we're going to practice we're going to practice with them for a little bit and just look at how we could change them. And what we'll do is we'll start with some binomials. So let's just take something really simple, x plus 2 times x plus 3. So when you learn about multiplying binomials, you realize that there are two terms here, right? They get multiplied against those two terms there. And you hear that we talk about foiling, right? Which means you got to make sure you multiply the first terms and the last terms. I'm going to show you a different, and then the outer, and then the inners, and then you combine all those terms together. I'm going to show you a different model for multiplying these binomials that I want you to think about, and this model is very helpful for me when it comes to factoring. So that model is to consider a room. I want you to think about a really simple room. And this room is just going to have dimensions of x by x. Okay? So what I would know is that if I wanted to find the area of the room, I would take x times x. That would give me x squared is my area of that room. Okay? So now what if that room had, let's say 2 more units length over this way, and let's say I had 3 more units length over that way. Then it would be a rectangle kind of like this, right? So we would do the same thing we did for this rectangle to find the area of all these other rectangles, right? So this rectangle has a width of x still, that's still x here, right? And a length here of 3, so we would call this 3x. We multiply this width x times this length 3. This one has a width of 2 and a length of 3, so 2 times 3, this would be 6. And then this one over here has a width of 2 and a length of x, so it would be 2x. So now what we've done is we've done foiling just in a kind of a different form. It's given us this visual model has helped me, and now I need to do is combine like terms. Well, out of all these spaces, right, they represent the area of these rooms. To get the area of the entire room, or rather the area of this big rectangle, I have to multiply all this times all that. Or I can take these little rooms and add them together. So I would write x squared plus 2x plus 3x plus 6, right? And then these two combine and become 5x plus 6. So what's the benefit of that? Why do we do this kind of multiplying using this model? Well, what if we were going the other way around? Okay, what if I was going to give you this expression and want you to find that expression? Okay, how would I do that? What would I do? Well, I'll give you an example. Let's take, let me just think here. X squared plus 10x plus 16. Okay? So now, for this problem, I'm going to look for factors. I want to factor this out. I want it to look like this, okay? A pair of binomials. I want to find a way to factor this out. Okay, so what I would do is I would say, okay, if I was factoring it out using this model, I would think to myself, pretty much I want this term here to be 16. That'd be, this bottom right corner is going to be 16. And this top right corner, I'm going to put x squared. And then the sum of these two has to add up to 10x. So the way they'll kind of talk about it is they'll say, I need two factors of 16. Okay, so they're two numbers. Let's call them m and n. Okay, such that when I multiply m times n, I get 16. But when I add m plus n, I get 10. So now I got to think, what are my factors of 16? Okay, so I'll make a little list here. Factors of 16. 1 times 16. 2 times 8. 4 times 4. And that's really all there is. So now I just look at these pairs and I say, which of these could add up to, they all multiply to 16, but which one of these that multiplies to 16, which one adds up to 10? Well, 4 times 4 does not add up to 10. 1 times 16 does not add up to 10. Or 1 plus 16 would not be 10. 2 plus 8, that's going to give me 10. So I could come over here and I could say, okay, if I had 2 times 8, that would give me 16 in this box. All right, that's a start to getting me where I need to go. I need x squared in the top box. Well, the easiest way for me to get there is just put x and x. So now am I going to get the rest of my expression here? I've got x squared and 16. When I multiply this area is x squared. When I multiply this area, I get 8 times 2 is 16. So now what would the area be here? Well, 8 times x is 8x. And the area here is 2 times x. That's 2x. And if I combine that all together, x squared plus 16 plus 8x plus 2x, those two are going to combine into 10x. And sure enough, I have found the factors. Now what does it look like? Well, these are x plus 8 and x plus 2. So I would write it out as x plus 8 times x plus 2. And these two are going to be equivalent. Now there's some things that you got to be aware of and you need to be careful about. The first being if this number is negative or if this number is negative. Okay? And possibly they both could be negative. Okay? You have to be very careful for that. You have to think about way many more of these possible combinations that could come along. You need to know that you can have, if I had 1 plus 16, that'd be, 17. But what if this was 1 plus negative 16, then it'd be negative 15. So you have to be very careful with that, thinking about your factors. You always have to consider whether or not they're going to be negative. Let me give you some tips. If this term is positive, then the signs here and here have to match. And if this sign is negative and this sign is positive, then they both must be negative, right? Because for this to be positive, they're both going to have to be negative to turn this positive. And they're both going to have to match to be positive. And if this is negative and they match, then they both must be negative. When this is positive and this is positive, okay, and they're both positive, then this is going to match and they're both going to be positive. But what about when this is negative? Well, when this is negative, then I know these signs are not going to match. And what I know is that this term right here, that if it's positive, then the larger of the two numbers must be the positive one. And if it's negative, then the larger of the two numbers must be the negative one. But if this is negative, again, the last term is negative, then it must match. Okay, so they often call this model here, instead of x squared plus 10x plus 16, they often call it ax squared plus bx plus c. And to factor it, we're looking for terms, right? Here it goes again. I'm looking for terms. I will use I'll use m and n again. So where m times n must be equal to c, but m plus n must be equal to b. And this rule only works when a is 1. And that's all I'm going to worry about for right now. I don't want you to worry about when a is not 1. When a is different from 1, well, things get a little more complicated. But I'm not going to get into that right now. Okay? All right, let's see. What else am I going to show you real quick? Oh, there's another little trick I want you to see. Sometimes when you're factoring, you're going to see some patterns. So one pattern you're going to see is you're going to see a pattern that looks like this. It's going to go like this. It's going to be like this. X squared minus 9. So this one is called the difference of squares. So this is a really nice pattern to recognize, the difference of squares. So when you're doing the difference of squares, what you're going to do is you take the square root of the first one, so the square root of x squared. There must be perfect squares, right? The difference of perfect squares, really. This must be a perfect square. So what we have is we have the square root of x squared is x, and then the square root of the last term is, which is 9, is going to be 3. So to factor this, it turns out there's a little pattern here which makes it really easy. You can just do x plus 3, x minus 3. X plus 3 times x minus 3. But all you're doing is you're noticing, hey, that's a perfect square, and that's a perfect square. So let me square root each one. So x squared becomes x, 9 becomes 3. That's taking the root of each of these perfect squares. And then I make two binomials. One is add and one is subtract. So this is a add and a subtract of this square. So this is a pattern. Give you an example. If I had x squared minus 25. Well, I would know that's the same thing as, watch this, x plus 5, x minus 5. And here's how it works. X times x would give me x squared. 5 times x would give me 5x. Negative 5 times x would be negative 5x. And negative 5 times 5 would give me negative 25. Well, these two are going to always cancel because they're identical, right? Their products are identical, but they're opposite signs, so they're always going to cancel. So I just end up with x squared, and then this perfect square in the back is always negative. So that's how I know I can follow that pattern, okay? That's one really, really important, good one to know. One more time, I'll show you it here. Let's say 4x squared minus 16. Well, this is a perfect square, that's a perfect square, so I'm going to take my perfect squares and I'm going to factor them out. 2x plus 4, 2x minus 4. And that would be my solution there for factoring. And the reason that works is 2 times 2 is 4, x times x is x squared. 4 times 2x is 8x. Negative 4 times 2x is negative 8x. And negative 4 times 4 is negative 16. So when these guys cancel, I'll end up with 4x squared minus 16. Okay? So this is how you can create equivalent expressions using factoring. Okay? One last one I'm going to show you. You may have a problem that is even a little bit hairier. So what you'll end up with is you'll end up something like this. ax squared plus bx plus c. And you're not going to be able to square it out. And so then what you're going to do is you can do something called completing the square with this expression. So you're completing the square. Okay? So what we do with this, see, is we go like this. And to do this, A must be equal to 1. A equals 1, all right? Otherwise, it gets a little more complicated. But what we do is we take our expression, right? Ax squared plus bx, and then we add in, we go plus b over 2 squared, and then we add c, and then we subtract b over 2 squared again. So now what we're doing is we're keeping this expression equivalent because we're adding something, but we're taking it right back. We add it, and then we take it right away. And this is really important because, this is why it's important, what I'm adding and what I'm subtracting are the same thing, so it does not change the expression. How it can help me is I can now group, this is called the associative property, and all I have to do is I look here at this terms and I do my factoring like we did above. I say, what do I need to get this term here, and what do I need to get that term down there? Okay, and then I need to make sure that they add, my factors for this have to add up to b. So then we can factor this part, and then that just becomes an extra part of the problem. So I'm not going to do a problem for you right now, but I want you to see that because I know you're going to run into that in your Khan Academy exercises. And now I'm going to take a moment and I'm going to have you see how we can prove all of this and do some factoring using technology, which is really, really cool.